side of ER. So I'm really looking forward to learning more about the quantum field theory aspect. So please.
Okay. All right. Thank you very much. And yeah, it sounds like the microphone is working, so I think I'm all set to go. So I wanted to, in this talk, give a review of the fundamental formulation of quantum field theory in curved space-time, and it's kind of the intended audience, or the central part of the intended audience, is really mathematicians who've taken at least a course in classical and quantum mechanics, but I hope this will be of interest to everyone else as well. So this, now it's not advancing. It was when I tested it. I can get by with just using, yeah. Yeah, okay, that works now. Okay, so first of all, what is quantum field theory in curved space-time? It's simply a theory where matter is treated fully in accord with the ideas of quantum field theory, but gravity is treated classically in accord with general relativity. And for the most part, that just means it's described by a space-time metric. So this sort of hybrid classical quantum theory is not expected to be, an exact theory of nature. It's not being proposed as that, but it should provide, one would hope, at least a good approximate description in circumstances where quantum effects of gravity itself don't play an important role. And despite the fact that we're not trying to treat gravity itself as a quantum theory in this, in quantum field theory in curved space-time, I think there's no question that it really has given us some of the deepest insights that we have into what properties quantum gravity must have. And I think the most striking of these is the prediction of particle creation of black holes by black holes that fit in with all of the thermodynamic ideas of black holes and are undoubtedly telling us a lot about the quantum states of black holes. But that's not what I'm going to be telling you about the quantum field theory in curved space-time. And in this talk, I'm going to be focusing not on the applications to physical processes like particle creation, which would be a long separate talk, but on the conceptual mathematical issues and its formulation. And indeed, by having to formulate quantum field theory in curved space-time, I think that really has provided some important insights into the nature of quantum field theory itself, because when one does it in flat space-time, there are various crutches like global Poincare invariance, ability to take global Fourier transforms, global notions of energy, and these give you a unique choice of vacuum state that usually play a key role in the formulation of quantum field theory, and one doesn't have those crutches here, so you're really forced to formulate the theory in a purely local manner and formulate it in terms of the properties of quantum fields. So to start with, let me consider, for the very start, classical physics of a system with finite number of degrees of freedom. Then I'll talk about a quantum system and harmonic oscillator, and then we'll talk about a quantum field, which is basically a harmonic oscillator with infinitely many degrees of freedom. So in classical physics, the states of a system are described by a point in phase. A state of a system is a point in phase space, which is a 2n-dimensional manifold. Observables are just functions on phase space. And the key additional structure one has in classical mechanics to the manifold structure of phase space is a symplectic two form, which is just a symplectic form, which is just a non-degenerate closed two form, which is automatically possessed in the usual cases where the phase space is taken to be the cotangent bundle of some configuration space. Now, the inverse of this symplectic form can be used to define a Poisson bracket structure on observables. And this Poisson bracket, or this inverse of the symplectic form, also defines the dynamics. You have to be given a Hamiltonian, which is an observable, a function on phase space, and its gradient acted upon by the inverse symplectic form gives you a Hamiltonian vector field that defines the dynamics. The dynamical trajectories are the integral curves of the Hamiltonian vector field. Now, the corresponding situation in quantum physics is incredibly different. States, instead of being points in phase space, are vectors in a Hilbert space. Observables, instead of being functions on phase space, are self-adjoint operators on the Hilbert space. And the key guiding idea relating the quantum theory to the classical theory is this correspondence between the commutator of the quantum observables and the Poisson bracket of the classical observables. The dynamics is also remarkably different. I mean, the Hamiltonian is now an operator. I mean, it's an observable, but it's a quantum observable. It's a self-adjoint operator. It generates a unitary group, and that unitary group, parameterized by time, defines the dynamics. And in the Schrodinger representation, which is usually what one sees, at least in quantum mechanics textbooks, at least in the initial parts, one thinks of this unitary operator as acting on the states, and the observables are just fixed operators. In the context of quantum field theory and in what I'll be talking about, it's much more useful to equivalently think of this unitary group generated by the Hamiltonian as acting on the operators, and the states are just fixed quantities. So I put hats on the quantum observables, but I'm only going to be talking about quantum observables from now on, so I'll drop the hats. Okay, so one of the simplest examples of a quantum system is the harmonic oscillator. So this is a one-dimensional harmonic oscillator with position coordinate q and momentum coordinate p classically, but now these are operators, and this is the Hamiltonian operator. And to understand the properties of the quantum system, it's very convenient to introduce this lowering operator and its adjoint, the raising operator, defined in this way, in which case the Hamiltonian takes this simple form, and you have these simple commutation relations between the Hamiltonian and the raising and lowering operators. You can solve this equation for the Heisenberg time evolution of A very easily, and then use this equation to solve for Q. And in the Heisenberg representation, the position operator, oscillates with its positive frequency part is related, is the lowering operator, and its negative frequency part is the raising operator. The ground state of the system is the state that's annihilated by the lowering operator, and all other states of the harmonic oscillator are obtained by successive applications of the raising operator to this ground state. Okay, so now if we go to the free Klein-Gordon field in flat space-time, so that is the equation of motion that I'm considering, in order to avoid a few awkward things, but this is not, not a swindle or not anything that's important in the end. I'm going to imagine, instead of being in Minkowski space-time, that space is a 3 torus, or I'm putting, or equivalently, I'm putting the system in a cubic box with periodic boundary conditions. And I can then define the Fourier modes of this field, and it's very convenient to do that, because if I do that, the field Hamiltonian takes the form of a each of these Fourier modes decouple from each other. There's no interaction. And the Hamiltonian is just a harmonic oscillator Hamiltonian for each Fourier mode. So a free Klein-Gordon field in flat space-time, well, at least in a box, is nothing more than an infinite collection of harmonic oscillators. So we can just quantize each harmonic oscillator to get the quantum field theory of this Klein-Gordon field. And then if we solve for, this is basically the Q of the harmonic oscillator that I was considering, but now we have this infinite number of Fourier modes, but it still has a positive frequency part, a negative frequency part. These are now, instead of lowering and raising operators, called annihilation and creation operators, but they're the same things. This is the sort of final expression that we get for the quantum field. But now there's a problem that has to do with this infinite sum. If you try to define this object at a definite point, this formula just doesn't make sense. It does not converge in any reasonable sense of convergence. But it does make sense and does appropriately converge if you average it with some smooth test function. So if you view this operator not as an operator defined at each space-time point, but as what people call an operator-valued distribution, well, a version of this formula suitably smeared with test functions does make perfect sense and is well defined. But that's going to create problems. In fact, that is what creates basically all the problems of quantum field theory. Well, all the problems that, I mean, it's not like there are no problems in classical field theory, but the ones that go beyond the kinds of problems you have in classical field theory, because the fact that this is distributional is going to make it not straightforward to take products of fields, and when we're going to have to take nonlinear functions of phi to describe interacting quantum fields, or even to describe things like stress energy tensor of a free field, because that's a nonlinear function of the quantum field. Now, we still have our ground state and our excited states that we get, but in quantum field theory, there's a new language that is introduced for these objects. The ground state, and now that means the ground state of all of the oscillators, is called the vacuum state. And the excited state that you get by applying n creation operators is called a state where you have n particles present. Now, this notion, well, of particles, I mean, it's defined here only for the free Klein-Gordon field, as I've explained. But if you have an interacting theory, then states of the field that one would normally consider, particularly consider in scattering experiments, may well be such that the field behaves like a free field at early and late times. And in that case, you're going to have a particle interpretation in this manner at early and late times. And the relationship between the early time particle content and the late time particle content is certainly something of considerable interest. That's what people are doing all the time in accelerator physics, and the S matrix is the unitary map relates the early and late time descriptions of the state. And well, again, this is enormously useful. And it's so useful and so successful that one might get the impression, especially if you call the subject particle physics, that the notion of particles is fundamental to quantum field theory. But as I'll be describing, that viewpoint is certainly not tenable when you get to quantum field theory in curved space-time. But what is the case is the itself, is the key observable. Well, there are many other observables besides the basic quantum field, but the theory should really be viewed as a quantum theory of these fields. Now, a couple of things I want to point out for later use as we're about to move to curved space-time. One is that if you ask what was the key thing that allowed us to do this kind of separation of the field into an annihilation part and a creation part, which itself then is directly related to defining a vacuum state and defining a notion of particles, it was really the notion of positive frequency that played a key role. And to have a notion of frequency, you really need a time translation symmetry. So this notion of particles very much relies on the presence of a time translation symmetry, which of course we won't have in a general curved space-time. Another thing I want to bring to your attention is we can, in the vacuum state, straightforwardly compute the expectation value, the vacuum expectation value of a product of fields. Of course, anytime I write down an X or a Y, these objects are really distribution. You should understand these as being smeared in with functions. And indeed, the right side here is manifestly distributional, because if I didn't have these epsilons in here, you wouldn't know what to do. I mean, this expression diverges when X and Y, this is the squared geodesic distance between X and Y. So it is zero, and this expression diverges. Therefore, when X and Y are connected by a null geodesic. But if you put in these I epsilons here and the epsilon squared there, this is a perfectly well-defined distribution. And this choice of regularization is, it's not a regularization, it's a computation of what this two-point function is, but the particular way the epsilons come in has to do with the positive and negative frequency splitting. I've written this down for a massless Klein-Gordon field. If there were a massive Klein-Gordon field, one would have a particular function up here, and you would also have a logarithmic term. I should also mention that this vacuum state is, well, Gaussian in its properties of its endpoint functions, the expectation value of all the odd endpoint functions vanish, and the expectation value of all the even endpoint functions are expressible in terms of the two-point function in a Gaussian kind of manner. Okay, so now we want to get to curved spacetime. And if we go to a stationary curved spacetime, then we can really just, I mean, norm of the killing field has to be bounded from below. There are other, we certainly need a globally hyperbolic spacetime. I mean, not quite any stationary spacetime, but basically, if we are in a stationary spacetime, we can just repeat the kind of thing we did that I was just showing you for Minkowski space-time, do a similar positive and negative frequency decomposition of the quantum field operator, define a ground state, which we'll call the vacuum state, define particles, and so on. And if you have a space-time that becomes asymptotically stationary in the past and future in a suitably strong sense, you could define notions of in and out vacua and particle states. I'm still only talking about the free, that is non-self-interacting quantum field in now a curved space-time. And you could talk about scattering. So all of this you could do in complete parallel to what you would do flat space. But we're interested in a lot of other spacetimes in general relativity, like cosmological spacetimes that start with a Big Bang singularity, spacetimes describing gravitational collapse to a black hole where there are singularities in the future, and there's, the field can into the black hole. So, we don't have a notion of positive frequency there for sure, and so on. And in a completely general, globally hyperbolic curved space-time, there doesn't seem to be any preferred notion of vacuum state or particles. In fact, I view this as very analogous. People have been trying, and I think even today, see people occasionally still trying to define a preferred notion of vacuum state or some preferred notion of particles in general spacetimes outside of this kind of class that I've already referred to. And, I view that as trying to do classical general relativity by finding a preferred coordinate system. I mean, when you've learned special relativity and now you're first learning general relativity, it's kind of, you learned in special relativity that there's the preferred global inertial coordinates. And if you use those, everything becomes sort of simple and nice in special relativity. So now we go to general relativity. Now we try to find, preferred coordinates for general relativity. Well, that is not a good and fruitful way of proceeding. And I would claim that in the quantum field theory and curved space-time case, quantum field theory is one of the few things that I think has the right name. It is the quantum theory of fields. It's not a theory of particles. And we should really be talking about local field observables, and the predictions of the theory should be formulated not in terms of how many particles of this or that type are around, but what the are for measuring various particular values of local field observables. There's but this isn't just a question of language. There's a more serious aspect to the issue of defining preferred notion of vacuum state or particles. If we had a unique choice of Hilbert space, then, you know, you could argue it would really, that would make it more analogous to this. I mean, you could say you like these coordinates, I could say I like these other coordinates, but if we do things correctly, we'll all get the same results. And if that were simply the case, this vacuum state choice and definition of particles must be a question of differing in terminology. But it's more serious than that because again, this is a reflection of the infinite number of degrees of freedom that you have, different Hilbert space constructions of quantum field theory and curved space-time, which you can make a Fock space once you've chosen a vacuum state and get a Hilbert space construction that way. But in curved space-time, this in general will give rise to unitarily inequivalent quantum field theories. You will not be able to make a correspondence of the states as you've described them in one of the constructions with the states you've described in the other construction, so that all the local field predictions are the same. So if you would try to proceed to define quantum field theory in curved space-time, you would have to, by the way people usually think about quantum mechanics, where you define a Hilbert space. Well, Hilbert spaces don't really have any structure other than dimensionality to them, but a representation of the quantum field on that Hilbert space, that's what really contains the information. If you were to start with a particular representation, you would have to make a choice and figure out which is the right one in the first place if you were to proceed in that usual way, which is the way people usually proceed in quantum mechanics. I mean, but it really seems like it's a terrible idea to have to restrict to one choice, and there isn't any obvious choice to make. So how can you formulate quantum field theory in curved space-time without having to make such a choice at the outset and maybe change your choice later when you realize that didn't give you the states you were interested in? Well, there's a remarkably simple answer to this question, which is just to formulate the theory in the algebraic approach. And the hard thing about the algebraic formulation that I'm going to give you, the hard thing is that it's so simple that it's hard to tell that I've formulated the theory when I'm done with it, because everything I'm going to say is really simple, but I'll try to explain why this is fully formulating the theory. So the idea is that I want to define an algebra that characterizes the properties of the quantum field. So the basic quantum field that I'm working with is this. Well, I'm recognizing now that this phi has to be thought of as a distribution, so it's a phi smeared with some arbitrary test function. And I can start with this object and the identity element and a star operation, and just formally write down all expressions that I get. I mean, this so-called free star algebra that's generated by this unit element and the I sub f. So I just write down all things of this sort. Okay, and now I impose the following relations on this algebra, or I consider the ideal, the two-sided ideal, generated by these equalities, and I factor by that ideal. So the relations that I want on this algebra is that the phi should be linear in the test function, the phi should be self-adjoint, so its star should just be the phi of the complex conjugate of f. It should satisfy the Klein-Gordon equation in curved space-time, so this is the distributional version of satisfying the Klein-Gordon equation. And then, very importantly, it should this goes back to the commutation relations that I started with near the beginning of the talk. This is really the position momentum commutation relation, but written in space-time form. So it says that the commutator of phi of f with phi of g is the advanced minus I times the advanced minus retarded Green's function smeared into f and g times the identity. So the algebra of the linear field observable field observables is defined completely on this slide. And you should notice that, the field observables are essentially, well, they're linear combinations of correlation functions of the field. Okay, so that's the algebra of observables. What are states, right? States, at the beginning of my talk, were vectors in a Hilbert space and so on. Okay, now a state is just going to be a linear map taking the algebra elements of the algebra that I just defined into the complex numbers. And very importantly and non-trivially, it has to satisfy this positivity condition. If you take omega of a star a, you get a real number, and not only just any real number, but a non-negative real number, and that's true for everything in the algebra. And this is a non-trivial relation to check because it's non-linear in the algebra. You can't just check it for a basis or anything. So that's a state. The interpretation of the state is that the number that you get is the expectation value of the observable in that state. Okay, now you might, if you've not seen this before, you might very legitimately wonder, what in the world does this have to do with anything in a quantum mechanics text? Well, one way is pretty straightforward. If I gave you a Hilbert space carrying a representation of this algebra, then if I take any vector Hilbert space and look at the map, take the expectation value of the representative operator in that state, that will give you a state in this sense. So any vector in any Hilbert space representation of the algebra is going to give you a state. Okay, but it might look like this state, this notion of states is going to give you a lot more crazy stuff that has nothing to do with states in the sense that I've nothing to do with states as vectors in a Hilbert space. But remarkably and very simply, again, that's not true. If I give you a state, you then define, well, not quite an inner product because it might not be non-degenerate, but you can define an inner product, a pre-inner product, by the inner product of A1 and A2, the algebra elements, is the omega of A star, A1 star, A2. And this will be positive, if A1 equals A2, this will be non-negative. It might be zero, but that's not a big deal. You can factor by the zero norm vectors, and then you can complete this space to get a Hilbert space. So I'm making a Hilbert space out of the algebra. I'm starting with the algebra, I'm using the state as an inner product and making a Hilbert space, but I not only get a Hilbert space, I get a representation of the algebra on the Hilbert space. Whoops, because I know how to multiply, an algebra element A acting on a state A2 here is just the algebra element A2, which is some element of the algebra, which is an element of the Hilbert space. So this is the Gelfand-Neymark-Siegel construction that I'm describing. And the vector in the Hilbert space that I've now constructed corresponding to the identity element then satisfies this relation. So that shows that every state in the algebraic sense is a state in the ordinary Hilbert space sense. So we're not getting anything qualitatively new. So what's the big deal? I mean, I just said every state in the algebraic sense corresponds to a state in the Hilbert space. Well, the big deal is now we don't have to make a choice of Hilbert space. We just define the algebra, we use the notion of states that I just defined, and that gives us all possible states and all possible Hilbert space constructions of the theory without having to make a choice at the outset. So, as I said, the hard thing is how simple this is, because this is the algebra, this is the notion of state, and now we've formulated quantum field theory in curved space. Of course, you might want to know the properties of lots of states. I mean, but that's, further work, but we've formulated it. I mean, if we've written down Einstein's equation, you still to do a lot of work to figure out properties of it, but at least that's now a calculation. It's not, we don't know what the theory is. So we have the theory, but we're not by any means done, because I've only, this algebra that I've defined is only containing a very limited class of observables. I mean, it's these sorts of observables that you get by taking products of field operators separately smeared at different points. But there are a lot of other observables, even if we're sticking to a non-self-interacting field. I might want to know things about the stress energy of that field. That's not in my algebra, because it's not a product of fields smeared, of smeared field operators. More non-trivially, we'd like to look at interacting quantum fields. Now, even in flat space-time, we only really know how to do calculations of things in nonlinear quantum field theory perturbatively, but these perturbative rules require that we be able to define polynomial expressions in the fields and define time-ordered products of them, because that's what comes into the formulas. So what we need to do if we're going to proceed in this way is enlarge the algebra so that it includes these polynomial expressions and time-ordered products. So that's not a trivial task. So let's just worry about the simplest case, which would be defining the square of a field. And here's where the problem that I mentioned on a very early slide comes in. We'd like to take phi at point x and square it. That would give us phi squared at point x. But this does not make any sense, because this object was a distribution, and we try to square it. So you might say, okay, well, let's take phi of f and square it. Well, sorry, let's define phi squared smeared with f. I mean, phi squared can't possibly be better than distributional, so phi squared of f. Well, I can make sense of phi of x, phi of y smeared into any smooth function of x and y. Why don't I just let this fn here approach a delta function, and maybe that will give me phi squared, that will converge and give me some phi squared of f. Well, this does not converge. Just get meaningless divergent results, so you're going to have to do some kind of infinite subtraction to be able to define this phi squared of f. Well, to start with, let's be less ambitious and just try to define the expectation value of phi squared of f for some state. I mean, I'm writing this instead of omega just to make this a little more familiar, but sorry, this is not a state in the algebra. This is a state on the algebra. I shouldn't have an element of sign here. But this is, I'm going to try to define omega acting on phi squared of f. Now, there are lots of states in this algebra, and some of them have more singular behavior at short distance than the Minkowski vacuum or nice n-particle states in Minkowski spacetime have. Those states, I think, are too singular to even try to define phi squared of f. It's pretty clear that you can't define it on all states in the algebra. But if you restrict consideration to Hadamard's, what I'll call Hadamard states, so if we look at the two-point function, this bracket here is the same as the omega acting on phi of x, phi of y, and again, this is distributional, so these are really smeared with test functions, but it's easier to write it with an x and y than with the test function and integrals. A Hadamard state is one for which, for x sufficiently near y, the two-point function takes this form. So remember, with a 1 here, that was just the two-point function of a massless scalar field in Minkowski spacetime, and that gets generalized in curved spacetime. Well, just like in the massive field, there will be a logarithmic term, but there'll be functions u and vn, which are certain locally constructed objects, which Hadamard locally constructed back in the 1920s. And then there'll be some remainder term, but this remainder term, if you go sufficiently high up in order here, will be sufficiently, well, smooth. I mean, Cn in this case. So if we have a Hadamard state, then we can subtract off this locally constructed part here. Well, there's some ambiguity in what you want to, well, I guess there's not any ambiguity actually in what you might want to consider in this part, but you subtract off this locally constructed part, and by definition of Hadamard state, you'll get something that's sufficiently smooth. I mean, in this case, Cn, and in that case, you can take the coincidence limit, and that will define the expectation value of phi squared. So this kind of Hadamard subtraction is the procedure used to define, well, in this case, phi squared, but you could do a similar procedure for higher order things. But I've only defined the expectation value. We want to do better than that. There is some non-uniqueness in this prescription, I should say, and in this case, we could add a multiple of the scalar curvature to phi squared. But well, let me move on. we want this thing to be an operator, not a quadratic form. We really want to enlarge the algebra of observables to include such things, not just have some formulas for expectation values, you know, if we're going to be able to do all the things in curved space-time that people are able to do in Minkowski space-time. So how in the world do we do that? Well, that's where 30 years ago, a major advance was made by realizing that the wavefront set technology is ideally suited to dealing with these issues in curved space-time. And, well, the result that got this started was a result of Marek Radzikowski's in 1996, where he showed that this very cumbersome Hadamard condition that's expressed here, but I have to talk about convex normal neighborhoods and no additional singularities and so on, and you know, well, this is all really rather complicated. But that was equivalent to the wavefront set of the expected two-point function in a state, in a Hadamard state, to being of this form. Now, the wavefront set, for people, physics people not familiar with it, is a refined characterization of the singularities of a distribution, where you not only characterize the points at which a distribution is singular, which is fairly straightforward to do, but you characterize the directions in momentum space where they're singular. And this is saying that this distribution is singular only when x, well, you can't really tell from, I haven't explained the notation properly, but when x1 and x2 are connected by a null geodesic, but importantly, the K1 is in the future light cone, and the K2 is the parallel transport of the K1 to K2. Well, K2 is minus that, and it's in the past light cone. And as I'll explain, this wavefront set characterization, as I will explain right in the next slides, can be used to define this enlarged algebra of observables. Well, no reason for you to think this has anything to do with anything you know, it would be helpful for anything I'm talking about, but I'll explain that in a minute. There's an interesting side note because in talking with Whiteman some years ago, issues in quantum field theory and curved space-time actually played a big role in some of the development of the wavefront set technology. In particular, you know, Hormander was I think, reading some of Bryce DeWitt's papers and trying to understand what a Feynman propagator in, well, flat for that matter, or curved time was. And, you know, in the paper of Dustermatt and Hormander, there's a discussion of, in their development of distinguished parametrices, they talk about the Feynman propagator and so on, and that, I think, really came from quantum field theory and curved space-time. So that technology has now come back in an extremely useful way. So how does that work? Well, here's how one can go about defining this enlarged algebra of observables. So to start with, we choose some Hadamard state. Any Hadamard state, it doesn't matter. I mean, you know, you don't have to carefully choose what you think is the vacuum state or anything. Choose any Hadamard state. This is really just to get going. And now using that Hadamard state, you can define what are referred to as normal ordered products of the field by appropriate subtractions of lower endpoint functions of the field with two-point functions. So the simplest case of a normal ordered product is the product of the normal order of the product of two fields, and that's defined by the formula I just gave, where you just subtract off this two-point function times the identity. So this isn't really doing anything. Defining this is not by itself doing anything, but we can now kind of change the basis of the algebra and use these objects rather than these objects or their endpoint functions as the basic elements. So we can rewrite any element of the original algebra in term, anything of this sort that we had in the algebra, and the algebra is just sums of those sorts of things, in terms of these normal ordered guys and this W naught. And then one can see that the commutation relations, which was a key part of this original algebra, can then be encoded in a formula for the product of two normal ordered products. So if I take, if I take the normal ordered x1, x2 times the normal ordered x3, x4, that will be equal to the normal ordered x1, x2, x3, x4, and then a whole bunch of other terms involving the W naught and things like that. Okay, but now the wavefront set properties, this wavefront set business comes in, because part of the technology with the wavefront set is rules for when it makes sense to take the product of distributions or convolutions of distributions for that matter. So just, I think you're all familiar with, if we have a delta function of the coordinate x, it doesn't make any sense to try to take delta of x squared. Okay, but if we have a delta function of x and a delta function of y, delta of x, delta of y times delta of y makes perfect sense, even though both of them are singular at the origin. That would follow from the rules, because of the directions of singularities of the delta of x and the delta of y, even though they're both singular at the origin, are different, and there's no problem, or they're appropriately different, and there's no problem taking their product. So using this we have wavefront set properties here. One can see that if you look at the product rules, the algebraic rules for defining this algebra, those rules, of course, make perfect sense when you smear in with smooth functions. But from the wavefront set rules, you can also see they make sense when you smear in with delta functions, well, times a smooth function. And if I take the endpoint, the normal ordered endpoint function, and smear in with this, that should be defining the normal ordered phi to the n. So we can enlarge the algebra by enlarging, instead of having to smear with test functions, we can now smear with a very wide class of distributions, and that's enough to allow us to define things like this. But what we really want is phi to the n, not normal ordered phi to the n. Normal ordered phi to the n depends on this choice of omega naught. It's an imposter for the thing that we're really looking for, which is the local field phi to the n. But we have this enlarged algebra of observables. The itself, by the way, does not depend on the choice of omega naught. If I chose a different omega naught, I'd get an isomorphic algebra. But now I have to look for what object in the algebra defines phi to the n. And a critical condition to impose is that the phi to the n depend in a local and covariant way on the metric. When that is imposed, you get a well-defined prescription for defining all polynomial observables in the field and its derivatives, but there are, ambiguities in the formula. I mean, one is familiar with renormalization ambiguities in flat space-time. Those actually come in only for the time-ordered products. Here, the ambiguities are all local curve type ambiguity. The definition of phi is ambiguous up to scalar curvature times the identity operator. Okay, by a much more technically involved analysis, one can also similarly show that there is a prescription for defining time-ordered products that's local and covariant. And there's a relatively long list of properties that one would want to have for time-ordered products. Right, in flat space-time quantum field books, what I'm telling you here, the whole story is just normal ordering, and you don't need wavefront set tech. Well, you probably do need some of that to easily show this is well defined, but that's an early chapter. The complicated renormalization theory is this time-ordered product situation, but the situation, the bottom line is the situation is the same as in Minkowski space-time at the end, except that you have more renormalization parameters appearing involving local curvature terms. So the bottom line here is that quantum field theory for free fields is completely well defined with, of course, these renormalization ambiguities, and interacting fields is perturbatively well defined. So the situation is just like Minkowski space-time. I have about 2 minutes left, I think, and I have 2 slides left, so let me spend 1 minute on this slide because it's so that takes care of the main story I wanted to tell you, but one would like to do a bit more in the theory because it would be of interest to know how the quantum field back reacts on the space-time. Right now, up to now, the space-time has been this inert fixed geometry that I'm putting the field into, but of course, if we have a black hole, it will be evaporating. The space-time will change as a result of these quantum field effects. And in the context of quantum field theory and curved space-time, it would be, well, one would postulate that this semi-classical Einstein equation would hold, or that is just what semi-classical theory would be asserting. And, then that satisfy this equation would be relevant. So I just want to point out that there's a major issue on this because I think deserves more thought, and this comes up in many other, a number of other similar contexts where one has some effective field theory that isn't supposed to be exact. This isn't supposed to be exact. Because this TAB depends non-locally on the metric, but also, in a sense, depends on higher derivatives of the metric than the Einstein tensor. So if you just wrote down this equation and tried to solve it as an initial value formulation, well, the non-locality will create problems, but you'll probably get a lot of very nonsensical solutions. Uh, and I think it's a very interesting issue as to how one should treat this equation or equations like this that arise in many other contexts where you have something that's an equation that's not supposed to be exact, that you have something that's supposed to be a small correction, but if you try to take this equation literally and try to literally solve it, you'll get nonsense. So how do you approximately solve it in a sensible way? Okay, so conclusions. What I've tried to explain is that the theory of a free quantum field theory in curved space-time can be given a completely rigorous formulation, and there's also well-defined notions of nonlinear field observables that are unique up to well-specified local curvature ambiguities. And again, perturbative interacting quantum field theory in curved space-time is as well defined as in Minkowski space-time, though there will be additional local curvature ambiguities. And finally, I should emphasize that we don't have, or I certainly don't have, a non-perturbative formulation of interacting quantum field theory in curved space-time, but I don't in flat space-time either. And of course, what I've told you is not providing at all a quantum theory of gravity itself. Okay, thank you.
Thanks for this very stimulating talk. So we have time for a couple of questions. Yeah.
Sorry. Quick question. So for the wavefront side, you parallel transport the K from X1 to X2, but we're in curved space-time. Is that the local curvature ambiguity?
No. Parallel transport is not problematic in curved space-time.
But it depends on the path you take.
No, but we parallel, X1 and X2 are connected by a null geodesic, and we parallel transport along that null geodesic.
You assume where this local curvature ambiguity comes?
No, well, really, we're writing down a list of conditions that we want pi squared to satisfy. And that list of conditions will allow, this ambiguity. So it's really, the ambiguity is really just coming from the only way we know how to define phi squared or more generally time-ordered products of polynomials in the field is to write down the conditions that we want these to satisfy. And then there are ambiguities. The ambiguities cannot be, cured by, there are ambiguities, similar ambiguities that occur in quantum field theory in flat space-time. The usual renormalization ambiguities are of a similar nature.
Thank you.
You said that in the talk you described this star algebraic framework for quantum field theory, and then went to discuss perturbative quantum field theory, in curved space-time. But it seems to me that the formulation you described doesn't really fit into star algebraic technique, because operators like pi squared or pi to any power are not bounded operators, don't have a norm, so they're not really part of a star algebraic formulation.
I'm only talking about a star algebra, no other structure.
Okay, so that's so you cannot really do, say, analysis with these algebras, like say continuous. You cannot do calculus with, say, functions with values
Yeah, I'm not sure I caught, it is normal for people to assume C-star algebra structure or even von Neumann algebra structure. I am not doing that in anything. I'm just doing this trivial star algebra that I'm generating at first just from a free star algebra, and then I'm enlarging the algebra.
But in particular, if, say, take one polynomial that you define in the field and another polynomial, try to multiply them, in
Yeah.
general, they're gonna be ill-defined because as usual, these are the usual UV divergences.
No, but it is well, it's well defined in this enlarged algebra. The enlarged, I really have an enlarged algebra. I can define phi to the 7th
No,
smeared with F.
I
And
just meant suppose take a phi normal ordered square and another phi normal ordered square.
Okay.
And try to multiply them. The result involves products of two distributions which may not be defined. Square
yeah,
of
but that's the
distribution-
whole point. I can smear those I start with the objects. I smear them into these delta function distributions that I know from the wavefront set technology are well defined. Maybe we should talk about that later.
Okay, we can take this for the